All right, so let's assume that you land a summer job working for some wholesale supplier of shipping boxes. Okay? It's a good gig, nice pay. For the most part, you're just answering phone calls from customers, but there's not a whole lot of customer complaints because the product is fairly simple and straightforward. Now, the idea is, let's assume that a customer does call one day. So you're sitting at your desk studying your calculus, and a customer calls in and they said, hey, I have a problem with my order. So I ordered a 16 by 16 by 3 inch box, right? Let's assume this is one of the company's best sellers. So the customer ordered a few of these shipping boxes, and the volume of a 16 by 16 by 3 inch shipping box should be 768 cubic inches. But your customer says, hey, we got a problem. I measured one of my shipping boxes, and I'm only getting 766 cubic inches. Interesting. So, is the product actually defective? In other words, should you alert somebody in the assembly line to go check their cutting machinery, calibrate it, make sure everything is operational, because the customer at least believes that they've been shorted a little bit of volume. But yet, let me ask something. So, but you, again, you're since you're in calculus, and you have reached a section in calculus where you're starting to understand a little bit about error and error propagation, you ask the customer, what did you use to measure these shipping boxes? All right, and the customer just says, oh, well, I just used a standard ruler. Then you proceed to inform the customer that, hey, look, every ruler, every measuring device has some built-in error. Does that make sense? Does it make sense to you that anytime you use some type of instrumentation to measure something, there is going to be error in the measurement? Now, the real question is this perceived error in volume really just a fact that, or really just a product of the error within the ruler that the customer is using, or is there actually a problem? So, okay, so let's continue with the analogy, right? So maybe you do a quick, let's just say a quick Google search on standard rulers, and you find that the built-in error, rate of error, right, for these rulers is, let's say, plus or minus 0.01 inches. Now, I have absolutely no idea what the built-in error is for standard rulers and yardsticks and etc. But I'm fairly positive we could find it, we could fact check and figure it out on the internet. So, do you agree with me that this ruler is, every time you measure, there is going to be an error, and the error for this particular measuring device is plus or minus 0.01 inches. So let's make sure we understand what that means. So clearly on your company's website, with this box, this shipping box, they claim that the length is, say, 16 inches, the width is 16 inches, and the height is 3 inches. So that the volume, obviously I've already highlighted that. That's how we get a volume of 768 cubic inches. Now, let's factor in this error rate for this ruler that your customer is using, right? So this would be plus or minus 0.01 inches. All right. Now let's try to make sense of what that would mean. So what I'm going to do is I'm going to go ahead and write 768, which is the true volume. And then what we're going to do is we're going to go ahead and figure out what the maximum error would be based on this ruler, and the minimum amount of error that would be. In other words, or let's think of it as the maximum amount of error either above or below the true volume. So let's see if you can follow me here. So we're gonna do a length times width times height 2 more times. So length times width times height. Only this time, let's go ahead, instead of doing 16 times 16 times 3, let's do 16 plus 0.01, right? So that's 16.01. Then 16 plus 0.01, so 16.01, and then 3 plus 0.01. All right, now, if you have a calculator handy, you can run those numbers. And while you're doing that, I'm going to subtract 0.01 inches. So now it would be 16 minus 0.01. So that would be 15.99 times 15.99 times 2.99. Okay. So if we have a calculator readily available and we do a little bit of multiplication, for 16.01 times 16.01 times 3.01, we should get 771.52 inches. Not inches, cubic inches. Let me go ahead and erase that. And now if we use the calculator and do 15.99 times 15.99 multiplied by 2.99, we get 764.48 cubic inches. So what does that mean for us? That means, so this is a volume, but this would be the maximum expected volume due to error. And this is also a volume, but this would be the minimum expected volume due to error. So with just a little bit of quick calculations, here's what you're about to tell your customer that's on the phone with you. Maybe the conversation goes something like this. Well, sir, madam, thank you for choosing our company. I've researched the error, built-in error for the standard ruler that you said you were using, to be 0.01 inches. That would mean the maximum expected error that you would get in volume would be 771.52 inches, and the minimum would be 764.48 inches. So based on what you told me when you first called, you said that when you measured, you got 766 cubic inches. But because 766 cubic inches falls within that range of 764 to 771, we can attribute this to the error in the ruler as opposed to the error in the actual volume of the box. Now, I don't know what the customer does from there. Maybe the customer says, can I speak to your manager? But this is interesting, right? So this is the idea of error analysis, and I'll stay here for just a second. I'll use, because you might hear me use a couple different terms, either in this lesson, or you may hear other individuals in everyday speech using these words. So words like precision or accuracy. And to stay here for just a second, you don't have to take any notes here, but the idea of precision is just how repeatable are the results when you continue to measure some object, right? So let me make sure you understand. So let's say that, let's do it this way. Let's assume that right now it's actually 77 degrees outside. Okay, but you have some type of, this is the worst thermometer ever in the world, by the way, don't use that thermometer. But let's assume that you have some type of thermometer that you're using to measure the temperature outside. And let's say you and your friend and your other colleagues, each of you goes and looks at or uses this type of thermometer to measure the temperature outside. And let's say that this is what each of you is getting. Every time each one, so there's a little bit of variation, but each one of you, as you can see, the cluster is fairly close together in the reading of the temperature. But let's assume for a second that the true temperature is actually up here. So in this particular case, you would be able to say that this thermometer is precise, right? Because the precision has to do with how close or how repeatable the results are when you continue to use this measuring device. But notice how, although it's precise, it's not accurate, right? I mean, the real temperature is up here. It's also possible to have accuracy without precision. I won't continue with this this tangent that I've gone off on, but do you understand that you can have precision without accuracy, you can have accuracy without precision, but each of those mean something different. Now, for our purposes, what we want to be able to do is we're going to introduce a new topic in calculus, which we call differentials. And differentials are extremely helpful in studying things like propagated error or in other types of approximation methods. So let me go ahead, and from here I want to go to the next page, and I want to try to show you the geometry of what we're talking about when we talk about differentials. I can recall when my first semester in calculus being introduced to this concept, and I don't think that I walked away with a very good understanding of it. It's just it wasn't sold very well, if you will. So let me see if I can sell the idea of differentials a little bit better. So let's start. So what I have some graph, the graph of some function that is drawn here. And the only thing that I have labeled so far is there is some value x that is, well, let's say it's of interest to us. Okay? Now, I don't know what this function actually is, f of x, yet, but for right now, I know that if I plug x into this function, then what I will get back out will be f of x, right? So you know the deal. If you want to know the y value, f of x, say, equals 2x. Well, you need to plug in an x first to get back out a y. Okay? Now, what I need you to imagine, like spatially, what I need you to imagine is that we have zoomed in really, 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 really close. Okay? Does that make sense to you? Like, we had to... We really zoomed into this graph to see the viewing window that we're looking at right now. All right. So what I'm going to do is I'm going to collect some information as I start to add to this graph. And you listen. I know for many, and I don't always fault you because you're busy. Many of you are going to want to skip to the part where you go to the how-to. And which is a shame, because if you just hang in there for a little bit longer, you're really truly going to understand what role differentials could in if were you in engineering, and you're not going to just learn another recipe, a cooking recipe that you're going to forget, right? So just do your best, hang in there, pause the video, take breaks if you have to, but let's see if we can understand the geometry. So as of right now, nothing special is happening. Point A is at x, f of x. And as I've mentioned already, we've zoomed in really close, and that's where this viewing window that we're at right now. And now what we're going to do is we're going to move a little bit, let's say slightly to the right of x. Okay? So this is going to be a new x value. Now, the question is, well, what would be the new x value? And the answer to that question is very simple. If I'm standing at x and then I just take a very tiny step to get to this new place, this new point on the x-axis, where I'm at now will depend on how big of a step I took, right? The distance. So we're going to call that distance between these two x values, we're going to call that delta x. So what does that delta x mean? That just means that's how big of a step you took. Okay? So now let's label this new point. So ready? Let's see if you can agree with me here. So I was at x, then I took a step that was a length of delta x. And now I'm at x plus how big of a step I took. So x plus delta x. Okay, so I haven't lost you yet, I know that. So you're still with me. So now here's another point on our graph. Let's label that as well. Let's call that point B. And now let's actually think about that. By the way, that's not a B. that's a D. just in case you forgot. All right, let's label point B. Ready? All right, so this is going to be some x value, comma, some y value. So the x value in this case is going to be x plus delta x. And what's the y value? Well, you know what the deal. You plug in to your function f to get back out your y value. So this is going to be f of x plus delta x. All right, so far, so good. And now, what I'm going to do is I'm going to show you something that's very interesting. So we're going to go back to point A, and we're going to assume that we know about point A. We know the x value and the f of x value. But what we don't know is the information about point B. You with me? So what I'm going to do is, remember, derivatives are very helpful for finding the slopes of tangent lines to curves, right? So in other words, I'm gonna draw this for real in just a second, but if I draw a tangent line to that curve at point A, now that's not a very good tangent line, but if I know the slope of this red curve, and this red curve is a line, so that would mean that the slope at every point on a line is exactly the same. So if I know the slope of this line, then I know the slope of this point. Why? Because the only thing that line I just drew and this function f have in common, the only thing they have in common is they both share this one point A. And if I know the slope of the line, then I'm going to know the slope of this point, because that is a point on that line. All right, so now let me do my best to try to draw this, this tangent. Okay, ready? So here we go. Beautiful. All right, so what is this blue line that I've drawn? Well, this is going to be f prime of x. Right? We use the derivatives to find slopes, and that would be your f prime of x. And now we're here. Are you ready? I've been building up for some time to get to where we are right now, and all I need you to do is put your phone away and look. Do you see how, let's look, I'm looking at this region right here. Do you see how your blue tangent line is really close to, is really close to this point B? Do you see, see what I'm saying? I mean, there's a little bit of error, right? There's a little bit of error in that blue, in the f prime of x. But do you see how we're very close? So the idea of this topic of differentials is that we're going to be able to use just a derivative and to approximate a new y value. And yes, we will be off a little bit, okay? There will be some assumed error. But as long as delta x, right? As long as delta x is really small, then our approximation is going to be very close. Now, what I've done so far is I've introduced just a little bit about an error analysis, and I've tried to break down some of the geometry of what we're going to be doing here. I haven't yet sold you on some of the things that you're going to be able to do with this. So what I want to do right now is start to collect some information. Okay? So let's go ahead and start to collect some information, and I'll have all of this written on the next page. So it's up to you if you want to write it as we go, but I'll have all of this written on the next page. Let's start with what is the change, what is the actual change in y, right? So you are standing at point A, right? And there you are, you started walking, and now you're at point B. So let's talk about how y changed, right? I mean, to go from point A to point B, clearly y changed. So the actual change in y, it's very simple, right? It's your second y value minus your first y value. So in this case, it's going to be f of x plus delta x. That's your second y value. And then you want to minus your first y value, and that'll tell you how much y actually changed. Let's do the same thing for delta x. So if you started off at point x and then you took a step in the positive direction and now you're at x plus delta x, if somebody says, well, how how big of a step did you take? Well, it's just your second x value minus your first x value. So this would be x plus delta x minus x. Do you see how if I drop those parentheses, do you see how your x and your negative x would cancel? Right? That makes sense. That makes perfect sense. Okay, so now I need to, I want you to agree with me that in this class, we have been using the notation that dy dx, that is a notation for the derivative, correct? And you've also seen me use f prime of x, right? You've seen me use both notations. So both of them are just two different notations for the derivative of with respect to x. Now I want to show you why this first notation is actually superior to this second notation. This first notation, this dy dx notation, is actually the Leibniz notation for derivatives. This f prime is not Newton's notation. Newton actually, it's been a while, Newton actually used dots over his variables, I believe, in order to represent the derivatives. But now let me try to show you what's going to happen here. Let's pretend like dy dx is a fraction for just a second. And as any fraction, I can multiply both sides of an equation by dx, which would just basically bring the dx to the right side of the equation, right? That makes sense. Seems a little bit gimmicky, but hold on. Stay with me. So now this section has to do with this dy, right? We've been using dy dx, but let's talk a little bit about just the dy and then a little bit about the dx. So as of right now, let's just give it a name. So the dy is what we call the differential. Okay, so this is, let me go ahead and write that in there. So this is the differential of y. And of course, I'll write it, but dx is the differential of x. Okay, so that's great. We've given it a name, but that doesn't actually explain to us what a differential of y actually is, and more importantly, why we should care, right? So let's go ahead and do that now. Let me start with just like an intuitive way of thinking about what dy is, and then I'm going to write how you would calculate dy. So an intuitive way for you to think about differential, because if somebody walks up to you and says, hey, what's the differential? What is dy? Right? If you find yourself tutoring, you could say it is the incremental change in y. Right? It's a estimate of the change in y, assuming that the change in x is really small. All right, so hold on, don't leave me yet. So dy is equal to, let's go back up to this graph. Remember, see how close that blue curve is? The blue line is, I'm sorry, to the to point B. We're close, right? There's a little bit of error here. So dy is defined as f prime of x dx. And now let me go ahead and write the most important part on this page here, which is basically or approximately equal to the change in y. Are you ready? I'm going to find a different color here. I think I'm going to have to do it. I'm going to have to go with lime green. So here's the actual change in y, right? To go from A to B, this is the actual change in y. This is the approximate change in y. We're off by a little bit, but the smaller you make delta x, the closer those two will be. So this, in other words, let me label it. This is the delta y, and this is the dy. So now the other and the last two things I'm going to write here. And again, these are going to be on the next page. So in this case, the dx is not what we're studying, right? Because we're gonna assume that the change in x is tiny. So for our purposes, we're just going to assume that the change in x is equal to delta x, right? Dx is equal to delta x. And finally, the very last little equation that we're going to use in this section is how do you use differentials to approximate the new y value? All right, did I lose you? Did you pick up your phone yet? Come back. dy is the approximate change in y. But how do I use that to approximate the new y? All right. So it's very simple. It's just going to be the sum of your first y value, f of x, plus dy, which is, so plus f prime of x dx. All right, your first y value plus dy is your approximate new y value. Okay, I'm going to go to the next page, and I told you it was going to be on the next page, but this is not the next page. So here is a breakdown of everything that I just said. So I'm going to leave this here for just a second, so in case you want to pause the video. And now, here's what we're going to do. So I'm going to break this section up into two videos, and here's what I'm going to do right now. Let me jump right in to compare, just jump right into finding differentials. And then on the next video, I'm going to show you how you can use what is written right here to do some really cool things like error propagation, relative errors, in finding, even if you wanted to approximate a square root, right? If somebody said, hey, what's the square root of 16.5, right? I'm going to show you how you can get a pretty darn good approximation without a calculator, obviously, using differentials. Ready? But for right now, for the rest of part A of this section, let's just do some quick problems so that you can see what's happened. See basically the overall method, okay? So first example says, let's let y equal x squared. And what we're asked to do is we're asked to find dy when x equals 1 and dx is equal to 0.01. Are you ready? So let's do this. It's going to be very easy for you. So y equals x squared. That means f of x is equal to x squared. We're also told that x is equal to 1, and we're told that dx is equal to 0.01. All right, are you ready? So let's go ahead and find, actually, let me write right here. What is dy? Well, you have to look back at your notes. Feel free to. dy is f prime of x multiplied by dx. All right, everything on the left side is what we know. Now let's start the solution process. So dy is going to be equal to f prime of x times dx. I need to know what f prime of x is first. Okay, so let's go ahead and take f prime of x. So if f of x equals x squared, then f prime of x is just equal to 2x. Okay, so dy is going to be equal to f prime of x. So let me go ahead and put a 2x there, right? F prime of x is 2x, and that's going to be multiplied by dx. Okay, let's plug in some numbers. We know what x is, so I'm going to plug the 1 in here for x. We know what dx is, so I'm going to plug 0.01 in for dx, and this is what we get. So this is going to be 2 times 1 times 0.01. All right, assuming my arithmetic is okay, we're going to get 0.02. So that is dy. That is the approximate change in y. Now, please, what did you just do? Well, you started at x is 1, and you moved to another, you took a step, okay? The step that you took was 0.01 in length. And now you're at a new y value. So this was your approximate change in the y value. What I'm circling right now is wrong. It is incorrect, but it's a very good approximation. It's very close. So let me show you how close it is. Well, the actual change in y, this is how much y actually changed, is just going to be the second y value minus the first y value. Well, that's f of 0.01 minus f of 1. So that's, let's see here. That is 1.01 squared minus 1 squared. All right, let's see here. I think, or at least what I have written down here is, so that is 1.01 times 1.01 minus 1. So this is the actual change in y, 0.0201. So what I wrote in yellow is the true change in y. What we wrote in blue was the approximate change in y. And I know what you're thinking. If I can find the real answer, why would I waste my time finding an approximation? And it's a very good question, and I'm going to answer it in this next video. So what's the last thing that I want to do for this video? So here's what I want to practice really quickly. So I'm going to practice the idea of, so let's go back, dy dx is equal to f prime of x. So what I want to practice right now is just simply finding the differential. So all you're going to do is very simple. Listen, very simple. You're going to take a derivative, and then you're going to bring the dx to the other side of the equation. To be honest, that is really what's going to happen. Ready? Let's do it really quickly. So we're gonna find dy for each of these. So if y is equal to x squared, then dy is going to be equal to the derivative of x squared, right, which is 2x, but then we're going to attach a dx. Right, we're bringing this dx to the right side of the equation. Okay, now all I'm going to do is, that is the gist of these. I don't mind doing the rest of them since we're here. dy equals, dy equals, dy equals, dy equals. You can pause the video really quickly if you'd like and try it. So what are we doing? That's the real question, right? Because why do you freeze up on math tests? Well, we freeze up on math tests because we do a whole lot of practice without ever paying attention to what we're doing. So what you're doing right now is you are finding differentials, okay? So in this case, dy would be 1/2 square root of x dx. Dy would be 2 cosine of x dx. And I'm not going to do the rest of these. These are derivatives that you can do in your own time. But just remember, take the derivative, bring the dx to the right side. So should be pretty good at this stuff by now. All right, and let's do just a couple more. Actually, we'll just do one more, and then we'll take a break and start the next part B. So again, look, find the differential. Man, can you just imagine? Can you imagine a student freezing up right now on a math test? They're like, oh no, I don't know what to do. I don't know how to start. Find the differential just means we're gonna take the derivative with respect to x, and we're gonna bring the dx to the right side of the equation. So here is the derivative of sine of 3x. That's just 3 cosine of 3x. And now, so that's the derivative, dy of dx. And now we're going to bring this dx to the right side of the equation, and then we have the differential. Pretty cool. dy dx, what does that do? That gives you slopes of tangent lines to curves. And what does dy do? That tells you approximately how much y changed, as long as dx is really small. Okay, let's go ahead and take a break, and I will see you in just a bit for the second part of this video.